Good morning, everybody. Can you all hear me?
Yeah.
Perfect, thank you. All right, so good morning, class number 2. We're going to start off today just by going back over some of the stuff yesterday, looking over the assignment that I had you do, and I'll take any questions regarding the handout that I gave you, so we could go over some of those questions too that you had difficulty with. So let's start off by going over the assignment. Here, sure. Hide. Perfect. So this one assignment. So this is the assignment that we were looking at today. Okay. So we'll take a look at those problems. I haven't had a chance to go in and give you all individual feedback, but I will be doing that this afternoon, so that shouldn't be a problem. But we'll take a look at the problems together just so we're all on the same page. All right, just put this way down. So here we have all right. So as we said before, the first thing that we're going to do is put our coefficients together. So we're going to do these two coefficients. So I'll multiply them together. I'll just put them in one bracket for now. And then I put all of these things here underneath the same root. So 12 times 6 times x to the 5. So here I can put these together as 20x to the 5. And here I can put what's under the root. Put these together. I want to separate them into fractions. So I have 4 times 3 times 3 times 2. These x's become x to the 6. So this I can take out, and this I can take out, and this I can take out. The only thing that's left is right here. Okay? So 20x to the 5 times 2. The 4 comes out as a 2. The 3's come out as a 3. And the x to the 6 comes out as x to the 3. And all we're left with is root of 2. Now we can put our numbers together. So 20 times 2 times 3 gives me 120. X to the 3 and x to the 5 gives me x to the 8 and root of 2. That would be our final answer. Questions about that?
Miss?
Yes.
Can't you do 12 times 6 and then break it down?
Absolutely. So that's not a problem. If you would prefer to do it that way, no problem at all. I just skipped that step because it's already somewhat broken down, so you can just break it down further. But if you chose to do it that way, that's no problem.
Okay, thank you.
Okay, so make sure you're muted, guys, just on a side note. Okay, so let's look at number 2. So number 2, we have 45x cubed, 32x cubed underneath. And here we have 18x squared root of 8x to the 4. So let's go with, here we have coefficients and here we have our radical. So the first thing we'll do is we can reduce this. reduce 45 and 18. We divide them both by 9, we get 5 over 2. We'll have 1x left on the top because we have x to the 3 and x to the 2. And we have one big root here. 2x to the 3 divided by 8x to the 4. So this actually reduces within our brackets. So we have 5x over 2. We have the root 32 divided by 8 is 4. We have x to the 4 on the bottom, x to the 3 on the top, so we just get over x. This 4 can come out. Square root of 4 is 2, so we get 5x times 2 divided by 2, and we have 1 over x. These 2 cancel out, so we get 5. Just like that. Are there any questions about this problem?
I got as my answer 5 the square root of x.
Here's someone talking, but I can't quite hear the question.
I got as my answer.
Yeah.
5 to the square root of x.
Okay, so that would be fine too. So here there is another root that you could have taken. So if you had of here decided to just deal with each of these individually, okay, what happens is instead of guessing that you didn't put them all under one root, you kind of took things out and then dealt with it.
Okay.
So in this case, if you just take this out directly, okay, so we'll just extend the page here. So we have 45x cubed. Okay, if we just look at each of the brackets and what we can take out first. In the first bracket, this breaks down to 4 times 4 times 2 and x squared. This one would break down to 4 times 2 and x to the 4. So now we want to take out everything that we can take out. So we can take out this 4, this x to the 4, both of these 4s, and the x to the 2. So before we even deal with the coefficients, we're going to get a 2 here, we're going to get a 2 here, we're going to get an x, we're left with a 2x. We have a 2 coming out from the bottom and an x2 coming out as well, and we're left with the root of 2. Now you can start to cancel things out. So I have 1, 2, if we put this together, we have 180 over 180 over 36. And one big bracket here with the roots. So these go away. This reduces to 5 over 1. Here our 2's go away. So we have 5 root x. This is a perfectly good solution. This for now is also a good solution. So just depending on which method you decided to go with, what your first move was, would determine what answer you get. When we look at what we're going to look at today, we'll find out that this is actually the best answer to this question. The other one isn't a complete answer, so we'll see why in not long, but if you've gotten either one for now, that would have been perfectly acceptable. Answer your question?
Yeah, thank you.
You're welcome. Any other questions about those two problems? Okay. Yep.
When we went back to the first time you did it, can you just go back to that page?
Yeah, sure, no problem.
Thanks. You see it's 4 over x. Is that because previously it was x to the 4?
Exactly. So here you had x to the 4 and you have x to the 3. So
Okay.
4 minus 3 is 1, and it goes on the bottom.
It's only one left. Okay, perfect. Thanks.
You're welcome.
How do I put the side chat on? The extra one. Yeah, the extra one.
Okay, so I'm hoping that you also got a chance to look at the assignment that I posted. Hopefully, if not, that's okay. Just make sure you're keeping up as much as possible. So are there any questions from the handout that you got yesterday? So we have the handout from class 1. Are there any issues from this that you'd like to go over? I'm taking your silence as a no. Okay, so just a couple quick reminders before we start off with the new material. So in the Google Classroom, a couple of different things have been posted. So like I said, obviously you got the link to the Hangout because you're all listening in. Solutions to that handout that I gave you have all been posted with the complete work done. So if you have any issues, you could always refer to that, or you can send me an email. That's fine as well. The other thing that we have here are the notes. Like I said, I posted the notes as of yesterday afternoon. So that'll happen every single day. It'll be after the class. The notes for the next day will be posted. So you have access to them as early as the afternoon, usually around 1 o'clock. So you can be completely prepared for those. Yesterday, because of the confusion with the note posting, I did post the complete solutions here with all of my writing on it. Everything that we did together, the blue, the problems, everything. From here on out, like I said, I'll be posting only the blank copy, so you are expected to follow along and write in the notes that you're missing. You do have access. So I have a YouTube channel. Okay, whoops, not that one. Hold on. YouTube. So all of our broadcasts are posted to my YouTube channel, so you can come and see if there's something you'd like to go back over. The videos are posted. So from class 1, you're group 1 if you're the 8:30 class. So this is the first class. You can go back and look at the lecture again if there was something that you missed, a problem you want to see done again, notes that you just didn't have time to finish copying down. So there's always that option if you want that option as well. So just a quick reminder on that. Anything else? Okay. So if there are no more questions on that, we'll just take a look at the schedule for the morning. So once again, if you have any online issues, you're not sure if you're registered in the right class, please, please, please get that fixed as soon as possible. Send me an email, call the summer school. Everyone's super helpful here, so they're more than willing to help you out with any issues that you have like that. And if I can help you, I would definitely like to do that. What I'm going to be doing right now is in the classroom, training 1, who is also me, is posting a link to a chat on the side. So if for some reason you don't have access to the chat because there's too many people and you find yourself not being able to talk or not being able to type, just click on the link that I posted in Google Classroom just now, or training 1 posted in Google Classroom. And it's a side chat that I have open that I can see. So I'll be able to answer your questions through there. So if there is a problem that you want to go over on the first handout, just let me know as soon as possible. We'll go over that. Otherwise, we'll start the new material. All right, fantastic. So I'm assuming we are ready. So just a quick review. Yesterday we introduced the idea of radicals. So radicals, we're dealing with roots, just a simple square root, and we have different operations that we can do with these roots, different properties that these roots follow, because technically those roots are exponents. So we have all these different rules that we have, all these different properties. So we talked about simplifying, just like with fractions, and then we talked about adding and multiplying and dividing. So now the last thing that we want to do with radicals, there are two more things that we want to do. So we're going to cover those today. So the first thing is adding and subtracting. So I'll let you copy down what you are missing, and then we'll talk about it.
What page is this in the notes?
So this is page 2 in the notes.
What's like the title?
Operations with radicals.
The numbers didn't print it. Okay, thanks.
Welcome.
This is what they gave me, but it doesn't match what you've given me.
Sorry, we just had a minute technical difficulty, just figuring out some class confusion. Okay, so we're all ready. I'll just go down a bit more just to make sure. Wait another 30 seconds. Okay. So we will have another couple seconds while I'm explaining, so don't panic. So the second last thing we're going to do with radicals are adding and subtracting. So just like with fractions, fractions and polynomials actually, you can only add or subtract something that we call a like term. So a like term, when we're talking about polynomials specifically, was the variable and the exponent combo, okay? So here I could add this 2 because the base was the same, okay? So we both had x and x to the 1. So we could just add the coefficients up and simplify this to 13x. But here, even though the base is the same, we have an x, we have an x, and we have an x here. Because the exponents are not the same, we have 3, 2, and 1, we cannot put these together. So that is a simplified expression. So with radicals, you can only add radicals when the radical itself, what is under the square root, is identical. But unfortunately, what we saw when we were simplifying radicals is sometimes we have this big thing that has a different appearance. But when we manipulate it and break it down, the radical is a lot simpler. So when at first it might not seem like we can add or subtract it, when we break it down and manipulate it, we might be able to. If bases are the same, the basis meaning the radicand, so what's underneath the root, then all we have to do are add or subtract the coefficients. And we simplify. Look at what this looks like. We have some examples here. So just basic example here, we have 6 root 14 and 7 root 14. What we're looking for are bases that are the same, okay? Once we have bases that are the same, we have the radicand that's identical. We have root 14 and root 14. That's like saying we have 6 apples and 7 apples. How many apples do we have in total? Well, we have 6 plus 7 apples. Our apples are root 14. Meaning we have 13 apples or 13 of root 14. Same thing here. We check our bases. They're both root of m. Because they're the same, we don't care about them. We care about the coefficients. We have 5 and we have negative 23, or 5 minus 23. So when we simplify this, when we put it together, we end up with negative 18 of whatever we have, which is root m. Move it up for one more second. Look, we see that, okay, our bases. We don't have the same base. We don't know that we cannot add or subtract them yet, because this is clearly not a simplified base. So we have to get as to this most simple case scenario as possible to really see the same radicand. Let's simplify the second one. So I can write 125 as 25 times 5. 25 can be taken out. The square root of 25 is? This can be put together. 7 root 5 plus 20 root 5. Now I have identical bases. Identical bases, I just take the coefficients and add them up. So I have 27 of whatever this is, it's root 5. Questions? Okay, I'll give you a minute or two to try this one out and then we'll do it together.
Miss?
Yep.
So, how did you get 27?
Once the
also you added them, you just simply added, yeah, after getting the common base, okay.
then it's like saying, who cares what the base is at this point? It could be apples, right? Oranges. I have 7 of something and I have 20 of something. How many do I have in total? I have 27 of those somethings.
Excuse me, Miss.
Yes.
How did you take out the 25, like, and then multiply 4 times 5?
So if we remember from yesterday, we were looking for numbers that can be easily square rooted. Right? So on the side here, when I have the root of 125, well, 125 could be written as 25 times 5. So far, so good.
Yeah.
So here, I could write this theoretically as the root of 25 times the root of 5. As we have that property where if we have a multiplication, it can be broken into different roots. What is the root of 25?
5.
Well, it's 5.
Oh, okay, I see.
Goes into that right there.
Oh, okay. Thank you very much.
You're welcome. so we'll take a look at this example here. Once again, the idea is the same. We look at the bases and we say, okay, well, they're not the same, but could I manipulate them to be the same? So we'll start off here. 25 can be written as 25 times 3. And then we have plus 9 root. Everything here can be taken out because the root of 25 is 5. And then we have the root of 3 underneath. 4 times 5, coincidentally, we have the same thing as before, becomes 20. And we have 9 root 3. Now that our bases are identical, we have the root 3 and the root 3. We can put them together, so we just take these coefficients and we add them, so we get 29 of 3.
Miss, I have a question regarding D.
Regarding D? Yes.
So out of 25, you only wrote 4 times 5 instead of 4 times 5 times 5. Well, why is that?
Because when you here take the square root of 25, it's only 1 5. So we're not actually just removing 25. We're actually saying, okay, well, this is the square root of 25. Well, what is the square root of 25? The square root of 25 is 5.
Yeah, sorry. Yeah, sorry.
No problem. Okay, so what we're going to do is we'll do number F. We'll do F together. I'll give you a minute or two to complete F. Same idea. I was asked quickly to go back to the notes part of the blue. Let me scroll up just a second. Step after. Just to make sure. So try letter F and then we'll go over it together. Okay, so let's take a quick look at this together. So we can do as of right now because our bases or our radicands are not identical. And it's possible that even after manipulation, they won't be identical, but we have to check. So this one can be written as 2x squared times x. So we remember when we're simplifying radicands that have variables, looking for even numbers. So an odd number can be separated into an even number and a 1. So that's what we want to do. It can be separated into 4 times 4 times 2. 5 can be separated into x to the 4, x to the 1. A whole bunch of things that can be taken out of the root. We have this, we're going to have the 8x here. Then we have the x squared that comes out as just 1x. Because we remember, when we take a variable, even number exponent, we just take that exponent and we divide by 2. Just erase that little mark here. 2, 2, 2, 2. And here we're going to take out everything that we can. This 4, the square root of 4 is 2. 4, same thing, square root of 4 is 2. This x to the 4 becomes x to the 2. And then we're just left with 2x under the root. So if I simplify my coefficients, here I get 8x squared, root of 2. Here I get 3 times 2 times 2. So we get 12x squared, root of 2x. So now we see our bases here, our radicals are identical. So all we have to do is we're going to take this coefficient and this coefficient and put them together. So we have x squared, 12x squared, and we have the root of 2x. Simplifying this, we can x squared and x squared. Get a 4x squared. We're still left with the root of 2x. Are there any questions about that problem? All right. Are we ready to move on from adding or subtracting, or do you want to see another example? So I'm going to take, your silence is saying you're ready to move on. If you want to see another example or you're not feeling confident yet, speak up.
Can we do one more example?
Absolutely.
Thank you.
Oh, we'll do H because it's the trickiest. Just gives us a little bit of last hurrah with this. Like I said, same thing though. We take it one step at a time. All right. So we have a quite different radicals. We're going to separate them. So 99 be divided by 9, which is what we want, 9 and 11. X here is an odd number. That's annoying to us, so we're going to separate it into 2 and 1. Is even. Keep it like that. 6 can also be divided by 11. The 5 is annoying to us, so we can say it's x to the 4 and x to the 1. We're just going to recopy our coefficients, and now we're going to see what we can take out. Third of 9 squared comes out as x, and we divide by 2, which gives me 1. 6 becomes y to the 2, which is 3. We're left with 11 and x under the root. We copy down our coefficient here. What can we take out of this one? Well, we can take out 16. The square root of 16 is 4. The 4 becomes x to the 2 because we take 4 and we divide it by 2. And that's all we can do. So we have x. We want to put our coefficients together because this big thing is not something I particularly want to be dealing with. And I have a 3, that gives me 21. I have an x and an x, gives me x squared. I have a y to the 3, and I'm left with 11x. I have a 4 and a 4, which means 16. I have an x squared, and I have a y to the 3. That's 11x. Now if we look, our bases are identical. We take these, we add them together. So 21x squared y cubed plus 16x squared y cubed. We put it in brackets, and we'll have the 11x on the side. Now the question is, now before we add these up, we also have to look to see if this is the same as this, because we cannot add terms that aren't alike. Squared y cubed. So I can just take these coefficients and add them up. 37 cubed root of 11. And I'm done. Any questions? All right. There's one last thing for us to do with radicals, and then we are done with radicals, which I'm sure makes us very, very happy. Okay. I'll you write down the blue, and then we'll go over what we have to go over. Really good question in the chat. So before we look at that, I just want to go take a look at this quickly. If you end up, after you've when I look, 3x is not the same as 2x. So there's nothing I and that would be your answer. Perfectly acceptable. We can only start putting things together if we get identical bases like we had over here. But if not, then we're good to go. This would be your final answer. So we'll go back over here. Okay. What we are going to do is what is called rationalizing the denominator. So we know with exponents, our final answer can never have a negative exponent. So before we give our final answer, if there's a negative exponent somewhere, for instance, if we have 2x over y to the negative 1, this is not an acceptable final answer. We have to deal with this before we give a final answer. We have a similar idea with radicals. So with radicals, it is improper to have a final answer containing a variable This is not acceptable. You cannot have this in the denominator. So denominator, we remember the bottom half of the fraction. So rationalizing the denominator is basically a way of getting rid of the radical at the bottom. So there are two different cases. So a thin radical at the bottom means that we have something like 2 over x. And we want to get rid of this so that our final answer is in proper form. Remember what we would do with fractions. If you wanted to add or subtract a fraction, you needed to get a common denominator. So you multiplied the top and the bottom. So by 2. So when multiplying the top and bottom by the same thing, I'm not same term as the denominator. What the root is. So let's just take a look at what this would look like. Root 5. For whatever reason, here is what we are. You cannot is everyone muted? Because I've got a message that someone can't hear me properly because there might be a mic that's on. So make sure you're all muted, please. And if you see someone unmuted, you can just mute each other. All right, so you see 3 over root 5. Here we have a radical, a root in a denominator. All I'm going to do is I'm going to say, well, I'm going to multiply this by root of 5. What happens when I do root of 5 times root of 5? Well, the top just goes together. We don't really care. But think about this. We don't have to do this step every time, but we can just to see it better. Here we have, because we have a product, we can put them together, which gives me 5 times 5 underneath one root. We were just working with the idea that if I have a pair of a number under the root, I can take it out as a single root. So if you type this in your calculator, root of 5 times root of 5, it's going to be 5. Root of 10, that gives you 10. You have the root of x times the root of x, that gives you x. Do you have to do this middle step every time? No, you don't. You can literally just go from here to here, but I wanted to show you why we can do this. So you have the root of something times the root of that same something. So that is the idea.
Yes.
Yes? You're cutting out. I can't hear you right now. Do you have a question?
Can you hear me?
Now I can, yes.
Oh, okay. Sorry, I just didn't hear the part of you explaining how come it's 5, and if you just multiply like the root of 5 times the root of 5.
Okay. Take this here. I'll just put this as a side note. This step. Root 5 over 5 times 5. Look at this. Either you can say, well, because we have a pair of numbers, it just comes out of the root. Look at this. As I have the root of 25. Well, what is the root of 25? Root of 25 is just here, it's the same principle. If I have the root of 10 times the root of 10, this is the root of 10 times 10. Root of 100, which is just 10. If I have the root of x, the root of x. This gives me the root of x times x squared, which we know comes out as just an x. So the idea is that whenever we multiply something by the exact same radical, just get whatever we had underneath the bracket as our solution.
Thank you.
Here, I wrote all over B, so we'll take a look at C. So we notice here we have the denominator. Oh, we have a root. I want to do here, get rid of that root underneath. So because we have this property, I'm going to multiply it by itself. So the root of 3 and the root of 3, like I said, if you want to, you can now skip this step and say, well, the root of 3 and the root of 3 just gives me 3. The root of 2 and the root of 3, so underneath one root, they can go together. So this just gives me 2 times 3 is 6. So the root of 3 is 6 over 3. The idea is, once again, if you type in this into your calculator, or this into your calculator, you get the same value. One of these is a proper answer and the other one is not.
Is it not 2?
Is not.
6 over 3?
You have this root that is on the 6 only and it doesn't have
Okay.
a separator between the two. Okay. Let's just do this example, but I'm going to change it to an x. I want to show you that it works the same if you have an x. Term underneath the root, it doesn't matter what that term is, we're just going to multiply by that same term. What happens here is I'm just going to bracket this first thing. Multiply by the root of x. Root of x is just, yeah. Once you have no radical on the bottom, you're good to go. You could simplify this if you want and say, well, this distributes to here, this distributes to here. Root of x minus the root of 3 times the root of x all over x. And here these can be put together. So it doesn't matter what you have on the bottom. Just multiply by the exact same radical. You're good to go. Questions about this?
Why can't you put all 3 terms together? Oh wait, never mind.
You okay with that?
Miss, I have a question actually.
Sure.
So, in the first one you wrote in blue, you wrote -1 with square root of 3. But then in the second one, you wrote just simply x. Where did you go from -1 or 1 minus to x?
Are we talking about this problem?
Yeah.
Okay. So here, up by root of x, right? So there's this middle step that I guess I skipped that I shouldn't have. So what happens here when I multiply is that this term multiplies by the first. So you get 1 times root of x. You get this times the second, which is root of 3 times root of x. This distributes in to each of the terms here. And then you can simplify it. So 1 times anything is just whatever that anything is. And here you can put the 3 and the x together. And then you get the x here. So when you get to this step, this just multiplies both terms within the bracket. It's that distribution property that you saw in Sec 3 when you're multiplying different values. Does that answer your question?
Yeah.
Okay, perfect. All right. So there's a second case of this, and this is the absolute last thing we'll be doing with radicals, which I'm sure is very exciting for some of you. I understand. So we're going to be rationalizing the denominator, but there is another case of what we could do. So I'm going to put the blue up, let you copy it, and then we'll go over it. All right, let's take a quick look at this. So again, we're rationalizing the denominator. So we're doing the same thing. We're getting rid of a root that is in the denominator. But the second case of this is when you have a binomial denominator, meaning that you have something like this. 2 terms, the denominator. If you try to do this the other way, you're just going to keep getting a radical over and over and over and over. You could do this all day and you're never going to fix your problem. So we do something else. So we are going to be using conjugate. So a conjugate of a binomial is the same binomial, opposite signs between the terms. For example, x plus 1. So the conjugate of that is going to be 1. You'll have a minus. Here you have 2x plus 6. The conjugate of that is you still have this 6 plus you have a minus. 5 minus x. The conjugate of that, you'd still have the 5. You still have the x, you have a plus. These are conjugates. So instead of just multiplying by the term, we rationalize the denominator when it is a binomial. We multiply the top and bottom by the conjugate of the denominator. So we're going to be using this idea. Okay. Oh, here we go. On the bottom here, have a denominator. It has, and it has a number, meaning that it is, how do we rationalize the denominator? Multiply by the conjugate. First term, and the second term, but in this case, I have a plus. And I do the same thing on the top. Do this properly from secondary 3, and we'll take a look at this again today when we're reviewing polynomials. Two terms, when you have two binomials that are multiplying each other, fill them, which means each term in the first polynomial or first binomial multiply by each term in the second. So I have root of 5 times root of 5, which, as we know, just turns into 5. We have this root of 5, positive 1, which gives us positive root of 5. Then we do the same thing with the second term. We have this multiplying this, minus root of 5, times negative 1, which gives us just a negative 1 here. And we have this root of 3 times the root of 5 plus 1. What ends up happening here? We do see roots still in the denominator. But what we notice here is that I have 5 minus root of 5, so they go away. Meaning that I have 5 minus 1 at the bottom. Notice that we have this times this, this times this. The two middle terms cancel out. So that just gives us the root of 3 times the root of 1 over 4. So let's try the second one. We see root.
Would you not multiply through the 3, the root of 3?
Sure.
Yeah.
You can, absolutely. So this would give you root of, here the 3 times the 5 would be 15. You would also just get root of 3, because you have the root of 3 times the 1 with the 4.
Right.
All right, for this example, same idea. You can't have something that has roots in the denominator. So I'm going to multiply by the conjugate. So I have the root of 3 minus the root of 2, so I'm going to do the root of 3 plus the root of 2. Do that as well. And gets a bracket. You get a bracket, you get a bracket, everybody gets a bracket. Notice that the top is just the root of 3 plus the root of 2 squared. Because we have something times it's, which means it's that something. At the bottom, we're going to do the same. The root of 3 times the root of 3 gives me just root of 3 times the root of 2, the root of 6. And remember, 3 times 2 underneath the root, minus root of 2 times the root of 3, which is the root of 6. We have a minus, excuse me, a minus. Root of 2 times the root of 2 is just 2. What happens here is that I have I'm adding something and I'm subtracting something, so those things go away. So I end up with the root of 3 plus the root of 2 all squared. And I just have 3 minus 2. Which we know is just 1. Over 1.
Miss,
Yes.
how did you get 6 minus 6?
So this step right here. Okay. A FOIL. 3 minus the root of 2. We do the first, which gives me just 3, because we have the root of something times the root of something. Here, then I get this one times this one. Gives me the root of 3 times the root of 2. I have this something times this something, which is minus the root of 2, root of 3. Finally, I have this one and this one, minus 2. So I have the 3, I have minus 2. What happens here, the root of 3, root of 2, that gives me the root of 6. Same thing here, minus the root of 6. And it doesn't really matter what this is. If I'm adding something and subtracting something, I give you $2 and then I steal $2 off of you. Nothing's happened. It's 0, right? So if I buy 2 apples, then I eat 2 apples. I have no apples left. So if I'm adding something and subtracting something, they disappear. Does that answer your question?
Yeah, thank you.
Welcome. Okay. So we're going to scoop down to E and F.
Wait, I didn't finish copying.
Sure. This part?
Yeah. No, sorry, it's the bottom part of it.
Sure.
Thank you.
Is the root of 5 to the power 2 over 1 acceptable?
So you actually cannot, because remember, underneath the root you have a 3 and underneath the root you have a 2. But according to our
Oh, it's different radicans.
yeah, exactly. Different radicals means you cannot
Okay.
put them together. So this would be an acceptable final.
I'm done copying if you want to continue.
Great. Okay, so we're going to scoop down to E and F. I'll do one of these with you, and then I'll let you try the other one on your own. So here we have a root in the denominator. So again, I'm going to multiply by the conjugate. So I'm going to bracket everything. Here I have the root of x, but not plus. I'm going to minus. I'm going to do the same thing on the top. So it doesn't matter, number, variable, anything it is, it doesn't matter. 5 multiplies here to give me 5 root of x. 5 times negative 4 is 20. So now we deal with this bottom. Now, what's the hang of this? Actually just write in. So we know that when we multiply conjugates, and we're going to see this in a little bit when we do some polynomial work, but when we multiply the conjugates, I just get the square of the first, so I get x minus the square of the second, 16. So when you're comfortable enough you can just jump from this step to this step. Until then, we'll just take a look at where this actually comes from. If you understand where this comes from, feel free to just jump right there. Okay? So here we get, once again, this one times this one, which gives me this one times this one, which gives me minus 4 root of x. This one times this one, which is plus 4 root of x. And finally, this one times this one, which is minus 16. Touching this top, I don't want to. I have the x. What happens here? I have the exact same thing that I'm subtracting, which means the middle terms go away. So bottom, I'm left with x minus 16. So like I said, once you're comfortable enough, if you can do jump from here to here, by all means, I don't need to see the work. If you understand that relationship, go for it. All right, I'm going to give you 2 minutes to try that one, and then we'll look at it together. All right, let's take a look at this together. So even if you're not done, you can either try to finish it by yourself or just jump in with us when you have a chance. Oh, same idea. Conjugate, root of 2x plus 3. Top and bottom. This one becomes a little bit more complicated, because on the top, you also have to do that foiling thing. So we'll do that first. X times the root of 2x gives you x root of 2x. Then you have the x times the 3, which gives you 3x. You then have the negative 1, the root of 2x, which makes minus 2x root of. Finally, you have the negative 1 with the positive 3, which gives you minus 3. All over. Bottom half. Root of 2x. Root of 2x gives you root of 2x and positive 3 gives you root 2x positive. Negative 3 with the root of 2x gives you minus 3 root 2x. And finally, this one with this one gives you negative 9. All you have to do now is simplify. So here, we're just going to leave the top as it is. You can do some simplifying, but your life would be really complicated. And I don't want to have to do that. Radicals are complicated enough. Then here, same idea is that if we're adding something and subtracting something, it goes away. You have 2x minus 9. Again, you want to jump to this. It's the square of the first. It's minus 3 times 3, which is minus 9. If you want to jump straight to that, feel free. Questions? All right, so very exciting. We are done with radicals, which is awesome because radicals are one of the hardest things we're going to do this course was radicals. So if you're a little unsure and you're panicking a little bit, please, 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 please don't. This is one of the harder things we're going to do. And don't forget you have all that CST material to fall back on, so it's not a problem. So now that's done. Let's move on to something a little bit easier. So we are going to do a very, very quick review of polynomials. So I have a lot of examples, but we're not going to do a lot of them just because this should be fresh enough in your mind. So I'll give you a minute or two to copy down the blue. We'll just take a quick look at it together, do a couple of quick examples before we get into the new material.
Can you scroll back up?
Sure. Here good?
Thanks. Sorry?
Is here good or higher than that?
Just a little higher. Like to the little chart. Perfect, thanks.
Welcome. Is that here good? All right, let's get started. So just to go over, like I said, this stuff should be reviewed, so we're just going to go over it quickly. So terms are combinations of coefficients, which are numbers, variables, and exponents. So when you have 2x to the 5, you have the 2 that is the coefficient, the x that is the variable, and the 5 that is the exponent. So you have a monomial, which is the product of an integer and a variable. So for example, negative 10 is your integer, variable is x to the 12. 14 b cubed c5 is a monomial because it's one term without an adding or a subtracting. So there are multiple variables. Here you have 2 over 4 x to the 5y. So 2 over 4, this can work, okay? The degree of a monomial is the sum of the exponents on the variables. For instance, here you have monomial, you have the exponent on the variable, which is 12. This is a degree of 12. Multiple variables here in the monomial, what you do is you take them and you add them. So that gives you n as your degree. And for this one, same thing, you have multiple variables. So you take the exponents. Now when you don't see the exponent, we remember that we have an exponent of 1. Add the 2 and that gives me 6. So that is the degree of a monomial. So one term and one term only. A polynomial, a term or an expression made up of different monomials added together. So for example, we have 20x cubed, x squared, and 6. The monomials, and they're all connected by adding or subtracting. So we have different names. So a monomial is actually a specific subset of a polynomial. So it's a one-term polynomial. A binomial is a two-termed polynomial, so only two, like a bicycle, 2 wheels. Trinomial is it has 3 terms. Tricycle, 3 wheels, 3 terms. So the degree of a polynomial is a little bit different than the degree of a monomial. For the degree of a polynomial, you identify, see we have all these different terms that would theoretically each have their own degree. So what you do is you identify the degree on each of the terms. Here we have 7. So this term has a degree of 7. We have a 5 here, a degree of 5. We have 4, so this one has a degree of 4. We have a 2. This one has a degree of 2. The degree of the polynomial is the biggest number. So in this case, the degree is 7. We do not add them up. We only add them up on one term at a time. So if we use this thinking for the second one, it's the same thing. But here we get 9 and 4, which is 13. Here we have 6 and we have 2, which is 8. And here we have 5 and 2, which is 7. So this term has a degree of 13. This term has a degree of 8. This term has a degree of 7. The degree of the polynomial is one of these numbers. The degree is 13.
Miss?
So far, so good? Yes.
So how do you decide which is the degree of an entire polynomial? Is it just the largest number?
That's it.
All right, and why is that the case? Like, why can't we, in the case of number 2, why can't we add 8 and 7? Why is it only the biggest number?
About the degree, you're talking about the highest exponent that the polynomial obtains. And that basically is the biggest number that the term has. Okay, so if, for instance, you guys saw quadratic throughout the year, okay? Or if you have a term 2x plus 3x plus 1. You graph this. It has a lot to do with the graphing of it, which we don't go into detail with these kind of polynomials, but just to give you a little explanation. We graph this. This has the form of a second degree because of this 2. It doesn't have the form of a third degree. Third degree has a completely different picture. This would have the form of a third degree, not a fourth degree. So the way the graph gets displayed always has to do with the biggest exponent. The properties of the polynomial, the graph of the polynomial, all have to do with just the biggest exponent on one of the terms. So you don't have to know all that, really and truly. All you have to know is take the biggest number, but that just gives you an idea about why. Okay?
Thanks.
You're welcome. All right. We're going to do a quick, oh boy, a little bit behind, but that's okay. Adding and subtracting, I'll give you a minute to write these down. So, like we said with radicals, you can only add or subtract like terms, which means that you have the exact same combination of variables and exponents. Once you do that, you just add the coefficients. For instance, here we look, we have an xy combo. We have a 2 on the x and a 5 on the y, which means that these are identical. So I add the coefficients. In this case, I have a 1 in front, I don't see, with 4 x squared y to the 5. That's simple. Check your variables and then add the coefficients. Second example, I look at this. A and I have a b in both, fantastic. But the a has a 3, a has a 4. do anything. Even if these were identical, which they're not, we're identical. Do anything. So this is actually your answer. Only add like terms. We good with that? Okay. We'll now quickly zip through multiplying. Okay, so when we're multiplying, there are two different cases. If we're multiplying a polynomial by a monomial, you just multiply each term of the polynomial by the monomial. Case 2, by a binomial, you're going to multiply each term of the second polynomial by each term of the first. So we just used this thinking, the FOIL idea, when we were doing radicals. So hopefully this is even fresher in our brains than it was before. For example, we'll do a couple of examples of these. Here we have a monomial and a polynomial. So what I'm going to do is I'm going to take the monomial and I'm going to multiply it by each term of the polynomial. Have here with 5x squared, and 12x squared. The 5 times 12 is 60. X and x squared is x cubed. Then I take the monomial and multiply by the second term. 5 times the negative 7, which is the negative 35. The x times the x, which is x squared. I have this one, and this one. Whoops, not that one. Good grief. The monomial with this one, and that gives me 5 times 3 is 15, 1x, which is fine, just the 1x. Multiplying by a monomial, you just take the monomial and multiply by each term in the polynomial. You have a binomial times a binomial. It's a little different. So we talked about this again. We just use this thinking with radicals. Each of the terms of the first and multiply them by each of the terms in the second. So this first 9x and I multiply it by 7x, which gives me 63x. Take the first term again and I multiply by the second term. That gives me minus 9x. I missed a squared on this one. If you see me make a mistake like that, feel free to jump in. Just checking to see if you're paying attention. Get the 3 with the 7, 21x. Finally, 3, negative 1 to give me minus 3. I can put these two terms together because the x doesn't go with anything, so it'll just stay. 9x, negative 9x and the 21x are going to give me 12x. The 3 doesn't go with anything.
Miss, it's 63. Not 6.
Mistake?
You wrote
3.
6x squared is 63.
There we go. Thank you. 63. We FOIL, and that is that. Everyone remember how to do this? Fantastic. So we'll talk about division by a monomial. This should be the last piece of review, and then we'll start just a quick piece of new material just to finish things up. So again, with dividing, just like with multiplying, there are two different cases. When you're dividing by a monomial, your life is a lot simpler and way more straightforward. If you're dividing by a binomial, which we'll look at in a second, way more complicated. But nothing to fear. So when you're dividing by a monomial, you're going to take each term of the numerator and divide by the denominator. I have thing by a monomial. So I'm going to take each of these terms individually and divide by this monomial. I have 20x to the 5 divided by 2x squared gives me 10x cubed. Then I take this 100x to the 4 and I divide by 2x squared. Well, 100 divided by 2 is 50. x4 divided by x2 is x cubed. Negative 12x cubed divided by 2x squared. Negative 12 divided by 2 is negative 6. X squared, x cubed divided by x squared is just x. And finally, here we have 8x squared divided by 2x squared to give me 4. So each of these terms individually divided by this one. All good? Fantastic. This is where it gets complicated. So I'll let you copy the notes down. Too small. All right. So this is where it gets a little bit more complicated.
Wait, Miss.
Still need a minute? Sure.
All right, I'm done.
Fantastic. All right. So here we go. This is where it gets a little bit more complicated. So when you're dividing a polynomial by a binomial, all of a sudden you're going to be doing long division. Now you haven't been asked to do long division since probably grade 3 or 4, so we're going to review that at the same time. So just in terms of terminology, we have dividend, which is what is being divided, which is doing the dividing, and the quotient, which is your answer. So terms that you need to be familiar with. We are going to be doing the same steps as normal long division. Now these steps may seem a little bit abstract for right now, but when we do examples, you'll see that we're following step by step every single time. You're going to divide the first term of the dividend by the first term of the divisor. Now when we're doing this, we're doing the dividing, this term doesn't really exist to us. Place that solution on top, multiply this divisor by each of the terms of the divisor by this new solution here on top. Subtract, and then repeat, and then repeat. So we'll take a look at what this looks like. Again, it's going to seem a little bit abstract for now, but when we do a couple of examples, hopefully it'll become a bit clearer. It is presented like this, doesn't matter. As soon as you see a binomial at the bottom, you need to be setting this up as a long division, okay? It says that you're going to take the first term of the divisor, the dividend, and divide by this first term here. 5x squared divided by 5x is just x. I'm going to line it up with my x term here, just to make my life take this new term, multiply each term of the divisor. So this and this. I'm going to line it up. 5x gives me 5x squared times negative 7 gives me minus 7x. And then you subtract. So these are actually the steps that you do with long division. You take the first number, divide it by this, you put the solution here, multiply and subtract. So all the same steps that we do with numerical long division, but we're doing it with polynomials instead. The idea here is that this first term should cancel out, because what is 5x squared minus 5x squared? This goes away. What is 3x plus negative 7x? That gives me 10x. I'm going to bring down the next term. Now, I repeat this process. I'm going to take this first term of my new polynomial, divide it by the first term here. So what is 10x? 5x. I multiply by each term, so 2 times 5x gives me 10x. 2 times negative 7 gives me negative 14. Subtract. I do this, x minus 10x, okay. 14 minus negative 14 gives me 0, meaning I have no remainder. We're going to do a ton of examples like this, okay, because it seems complicated and overwhelming, but you're going to see it's the same step every time. First term, divide, multiply, subtract. First term, divide, multiply, subtract.
How did you get 10x when it's plus 3x minus 7x?
Well, plus 3 minus 7 minus negative 7. We have a minus negative, so 3
Wait.
plus 7.
But where did that negative sign come from?
This one, or this one.
The one outside the bracket.
You subtract, that's the rule.
Oh, okay.
So after you multiply, you're going to subtract what you've gotten.
Okay.
You always have this negative outside what you've multiplied together. always subtracting. So if you remember, if you try to do a problem by long division with numbers, this is what you did too. You were long dividing, and when you would do the multiplication, your next step would be the subtraction. Okay? So let's take another look. We're going to do pretty much 3 more examples, hopefully until the end, just to give you an idea of what's going on. All right, so we're going to go down to number 3, and then I'll talk about number 2. So like I said, anytime you see this, write it out, long division. So you have x, I want to use blue. I'll use black. Doesn't really matter. X minus 1, and you have 2x cubed plus x squared minus 8x plus 5. Long division. First step is you take the polynomial divided by the first term of the divisor, divided by x gives you x squared. Since it's an x squared, you line it up with the x squared term here. I then multiply, so I take this 2x squared, which gives me 2x cubed. And then here I multiply. 2x squared times negative 1 gives me negative 2x squared. Remember that I subtract. So 2x cubed minus 2x cubed, these go away. 1, I have this 1, minus negative 2 gives me 1 plus 2, gives me 3x squared. Need another term, so I bring this down. Process. Divide this. So 3x squared gives me 3x, and I line it up with the x term. 3x times x gives me 3x squared. X times negative 1 minus 3x. Subtract. Squared minus 3x squared, these go away. Negative 8 minus negative 3 means negative 8. 3 gives me negative 5x. I'm going to bring this down. One last time, I'm going to take this and divide by this. Negative 5x divided by x gives me negative. Here, multiply, negative 5 times x gives me negative 5. Negative 5 times negative 1 gives me positive 5. I'm going to subtract. Negative 5x minus negative 5 gives me nothing. 5 minus 5 gives me 0, so there's no remainder. So the solution is squared plus 3x minus 5. All right, let's take a look at one more. Look at number 2 on the next page. I'll just do one more very, very quickly. All right, same steps. This divided by this. 2x cubed divided by 2x gives me squared. I multiply here. So x squared times 2x gives me 2x. X squared times 6 gives me 6x squared. subtract. So the 2x cubed minus 2x cubed goes away. 4x squared minus 6x squared gives me negative 2x squared. And I bring down the next term. Take this term, negative 2x squared. 2x gives me negative x. Negative x times 2x gives me negative 2x squared. Negative x times 6, negative 6x. I subtract. Negative 2x squared minus negative 2x squared cancels out. Negative 10 minus negative 6 means negative 10 plus 6 is negative 4x. And this comes down. This term divided by this term, negative 4x divided by 2x gives me negative 5. Negative 2 times negative 2x gives me negative 4x. Times 6, negative 12. Subtract, and that gives me 0. So here is what is going to happen. So we didn't get through as many examples as I would have liked. So the assignment and the handout that you have for today that will be released probably in the next 10 minutes. There is a Google form here in the instructions for you to fill out and an assignment. I'm going to let you have until Thursday to do it just so that tomorrow we can spend a lot of the time going over this stuff. Okay, so don't worry about this. If you're not understanding it completely, we're going to spend at least a half an hour tomorrow going over it together when we see each other. And then you can fill these out for Thursday when you have a bit more of a basis. There is a handout as well that will be posted. You can take a look at that, or you can wait until tomorrow. Some of it has to do with radicals and review of polynomials, so you should be able to handle that. So that is all you should be doing tonight, is doing as many problems from the handout as you can. And if you feel comfortable trying some more of these, you can. For tomorrow's class, the notes will be posted. Take the time, print them out, bring them in. If you don't have time to print them out, I'll have some copies, but I'm hoping that you all will. Those notes will be posted this afternoon, so take a look for those. So bring the notes from today and the notes for tomorrow in class tomorrow so we can go over as many of those as possible. Sound good?
Yeah.
If you have any questions between now and then, feel free to post in the Google Classroom or send me an email. If not, I look forward to meeting you all face-to-face tomorrow. Have a good afternoon.
Thank you. You too, miss.
Thank you.